Okay. Hello. Welcome. I hope you're ready to continue. Today we are going to finish SIMT processors very quickly, and after that we will talk about graphics processing unit, and after that we will start the weekend. So that's the plan for today. The first thing that we are going to take a look at, we will quickly recall some of the concepts that we introduced yesterday, and then we will recall something else that was covered in previous lectures, but it's important to keep that in mind for the rest of the lecture. Remember that we are right now here, other execution paradigms, after having talked about single cycle, multi-cycle machine, pipelining, and out-of-order execution. And among these other execution paradigms, we find very long instruction war architectures, fine-grained multithreading, systolic arrays, decoupled access execute, and now we are with the SIMT processing and the GPUs. These are the required readings. One required, and the other one is recommended. Both are very important for today's lecture. We are going to actually start with the recommended one, because the first thing that we are going to talk about is about the SIMT extensions in current CPUs, and then we will start with the GPU architecture. So remember, SIMT processors are very good at exploiting regular data parallelism. They are not so good for irregular data parallelism, even though somehow GPUs are a little bit, let's say, closing this gap, because they have some interesting features that we are going to describe today. Also recall that SIMT processors and also GPUs correspond to one of the 4 categories, SIMT, that Mike Flynn introduced or described in his paper in 1966. The 4 categories are single instruction, single data. The best example is a sequential CPU. SIMT, we have array processors, vector processors, and GPU, and a special combination of both. Then we have multiple instruction, single data architectures, and finally, multiple instruction, multiple data architectures, where we can have multiprocessors or multi-core processors these days. Okay, so let's continue with that. In SIMT processing, recall in these SIMT processors, we have multiple processing elements, and the way that we are going to use these multiple processing elements will depend on what we call the time-space duality, which actually helped us to differentiate between array processors and vector processors. And you, I'm pretty sure you remember this slide, the comparison between array processors and vector processors. In array processors, we have an array of processing elements, each of which can execute different types of instructions. In this case, for example, load, add, multiply, and store are executed on the same processing element. So in the same time, as you can see, in the same time, we have the same operation in different processing elements. In the case of the vector processor, we have kind of specialized processing elements, and each of them is executing a particular type of instruction. So here, in the same cycle, in the same time, we have different operations executing in the SIMT processor. So yeah, that's the time and space duality. In the same space, in the array processor, we have different operations. In the same space, in the vector processor, we have the same operation. We were also talking about memory banking, because if we want the SIMT processor to be efficient, we need to have an efficient access to memory. Why is that? Because in memory, it's where we have the operands, where we read data from and we write to the results. And we have a lot of multiple processing elements. So in order to feed all these multiple processing elements, we need to have a very efficient access to memory. And the way of doing that is having a multi-banked memory. The good thing here is that we can be accessing all the banks at the same time, and we can issue one request to each of these banks in each cycle. Recall also that one problem that we can have is that we cannot be, in principle, with this configuration, we cannot be performing two accesses at the same time to the same memory bank, right? So if we really want to be efficient, what we could do is having more than one port, which means that we will have more than one memory data register and more than one memory address register per bank, right? So that's a way of, in this case, we will be doubling the bandwidth, right? And I got a very nice question, very good question at the end of the lecture yesterday. And the question was, what happens, I mean, we can put there more ports, right, in each of the banks. But what happens because with the data bus and the address bus, because we can still have only, let's say, one single data element in the data bus, right? That's a good question. Keep in mind that we don't describe the very exact details of how things are implemented in computing systems. But it's very good that you ask yourself these questions, because that's actually the way that it should be for us to be able to improve computing systems, right? And so I can have two possible answers for this. One possible answer is that we are not talking about what's the width of the data bus here, right? So if the element that we are reading from the bank has, let's say, 32 banks, but the width of our data bus is 64 bits, we can have two elements at the same time on the data bus. That's one possible answer. Another possible answer is that both components of the system can be working at a different frequency. And if the frequency of the data bus is higher than the frequency of the memory, we can also be able to issue more, to move more data around, right? Do you have any question?
Yeah, if we were to have two MARs and two MDRs, would the data from the memory be fetched also in parallel, or would we just load two MDRs or two MARs at once, and they would do the work just sequentially?
That's related to what I just said, right? To what I just explained.
I mean, within the memory, would we do two memory accesses based on the two MARs at the same time?
Yeah, exactly. That's the idea. Having two ports means that you are going to have two MARs, two addresses that are being accessed at the same time. That's the idea. Okay, any other question? Okay, yeah. We also talked about this slide yesterday. We have one instruction, a vector addition, A plus B equals C. This is a vector instruction, and you know that every time that we want to execute a vector program, we first need to define what's the vector length, right? But this vector length, it's more, let's say that it could be more like a software concept, because the way that the different elements that are going to be computed with the vector instruction are going to be executed on the hardware will depend on the hardware that we have, right? So for example, on the left-hand side, you see a pipeline ALU, a pipeline functional unit, where in each cycle we start the execution of the addition A plus B for the corresponding element. So in this case, you see C0, C1, C2, and so on. In every cycle, we will be obtaining one result. In this case, what we have is 4 functional units that can be working in parallel. But observe that the number of inputs that we have there, it's actually in total is 28, right? So what we are doing here is that we are distributing the computation, all the input elements that we need to operate on, we are distributing them in space and in time. So we are taking advantage of the pipeline design of each of these functional units, and also at the same time, we're taking advantage of the fact that we have more than one functional unit. And we also described this slide in which you can see what are called the vector lanes. Each of these columns that you can see here is called a lane. And in this lane, we can have 1, 2, or maybe more functional units. Observe also that each lane has access to a certain number of registers. So in the end, what we have here is like a huge register file, and every time that we are going to execute some program, we will distribute all the registers in the register file among the different lanes, such that the different vector elements are going to be placed in the corresponding registers, the registers that correspond to each of the lanes. Related to this, and also related to the previous slide, we very quickly showed in the very last minute this slide, where actually I think it should be useful to understand what's the difference between the vector length and the actual number of lanes. So in this example, we are considering that we have 32 elements per vector register. So assume that your vector length is 32. But the number of lanes that we really have is not 32, it's 8 in this case. So it's as if we had, instead of 4 of these elements here, we would have 8 of these elements. So what this means is that in every single cycle, we cannot execute the operation for the 32 input elements. We can only operate on 8 input elements. So if we want to issue one load instruction on the load unit for the 32 elements of the vector registers, we will have to do something like this. In the very first cycle, we start the execution for 8 of the vector elements, then for the next 8, and then for the next 8. In total, we need 4 cycles to execute or at least issue the entire instruction on the load unit. This number of cycles, 4 in this case, is called chime. Remember that in the next cycle, we can start also issuing another instruction in another unit, in this case, a multiply unit, and then the add unit. And as soon as we finish the load instruction, the first load instruction, we can start the execution of a second load instruction, and then another multiply instruction, and then another add instruction. Observe that in one single cycle, here, we are, how many, where is my, okay, I can see it now. We are executing like 24 operations in one single cycle, right? And in total, here in this toy example, we are executing 192 operations in 10 cycles. So it's quite productive, I could say, very, very fast. Okay, let's continue. I think we also talked yesterday about vectorization. What does it mean? It means that if we have some sequential code, like the code segment that you can see, or these 2 lines of code that you can see there, that essentially are a vector addition, 2 vectors of size n. We are adding element-wise and storing the result in C. Well, if we have a code like this, we could do some kind of loop dependence analysis, and if there's no, or a compiler could do, I mean, a smart programmer can do it, and a compiler can also do it, right? Some sort of loop dependence analysis, and if there is no dependency across iterations of the loop, we can vectorize this code, and finally the code will look like something like this that you have on the right, and each of these rectangles that you see here, they are each of the vector instructions, right? So we start with one vector load, after that another vector load, then vector add, and vector store. We are going to see this slide again a couple of times today. And the summary, we already finished here. What we were supposed to finish yesterday is this slide in which, I mean, it's just like a summary for you to recall that SIMD machines are very good for regular data parallelism, We can obtain a lot of performance improvement by vectorizing the code, by writing the code in a vectorized manner. But remember Amdahl's law. It won't be possible to parallelize everything, to vectorize everything. I mean, maybe in some codes for sure, but probably not in all real-world codes. So we will always have some sequential fraction of the application that is going to limit what's the maximum speed up that we can get from a vector matching because of Amdahl's law. Yeah, yesterday we were talking about some example of vector matching. We show some schematic of this Cray one and also the picture about the Cray that we have in the CAB building. These days, where you can find SIMD operations using like multimedia, what are called the multimedia extensions in current CPUs, right? Like, for example, these ones that you can see in the slide. And actually, that's what we are going to talk next, about the SIMD operations in modern ISAs. And in particular, we are going to talk about MMX instructions in Intel x86 processors. So you already know that SIMD operations are good, SIMD instructions are good to whenever we have a lot of regular code, regular operations, regular parallelism. And for example, one field where we can find this is graphics processing. Or image processing, right? Why is that? Because in the end, we are operating on images, and an image is composed of many pixels, many 100,000 or even millions of pixels, and we typically in this kind of computation, we apply the same computation on the same pixel. So that is why SIMD processors are very good, and these SIMD ISA extensions are very good for graphics and for image processing. And actually, that's what they noticed, the designers, computer designers in the 90s, when they started introducing these SIMD extensions in CPUs. And the reason why they decided to do that is because multimedia applications started to be more and more popular. I mean, maybe 30 years ago or 40 years ago, they were not so popular. In the 90s, they started to be very popular. So that's why some designers decided to, okay, why don't we modify our architecture a little bit and we introduce some sort of new capability to take advantage of what we already have in the system, but modify it in a way that we can execute SIMD operations as well. And here you have a very nice example. You have here three 32-bit registers, and observe that these three registers are divided into pieces of 8 bits. In the end, what these SIMD instructions do is that they operate using the same registers that the machine already have. You know that in a real-world processor, we have 32-bit registers or 64-bit registers. So what we do here is that we divide them, in this particular case, in 4 pieces of each bits each. And we can we can perform the computation on every piece of 8 bits. The only thing that we need to do is modifying the ALU to avoid carries between consecutive 8-bit values. So we don't need to carry the carry out bit from bit 7 to bit 8, right? But if we do that, we can have 4 operations in parallel. And this is what it's called a P-add-8. It's a pack-add. So they are called pack-add because in the same addition we have, in this case, 4 additions. So yeah, a little bit more about that. One instruction can operate simultaneously on multiple data elements, and it's not only the example that we have seen in the previous slide. Actually, here, the way that we can use each of these 64-bit registers is with each of these 4 configurations that we have here. So depending on what's the opcode, for some reason, okay, now I see it. Depending on what's the opcode, the specific operation code that we have in the instruction, the hardware will use each of these registers as 8 8-bit bytes, or 4 16-bit words, or 2 32-bit double words, or as one single 64-bit word. The stride is always 1, so this is a limitation of these SIMT extensions. It's different from what we were discussing today, and observe also that we don't need to define a vector length. And why is that? Because somehow implicitly in the operation code, we are defining what's the vector length, right? It can be 8, 4, or 2. And here we have one example of use of MMX. This example you can find, let's say, like the complete explanation in the recommended paper, but it's a really nice example to see how efficient these MMX extensions can be for image processing. In this particular case, in the example, what we have is, you know, like for example, when you watch on TV the weather forecast, you know that there is a weatherman or weatherwoman, and behind the guy or the woman, what you see is the map of Switzerland, of Canton Zürich or whatever, and some suns, clouds, many clouds this week. And but the truth is that that's not there. You know that, right? Switzerland is not right behind this guy. What this guy has is a chroma. What is called a chroma is just a surface with one single color, typically green or blue or something like that. So in this particular case, in this example, the background behind the woman is blue, and what we want to do is put, let's say, the shape of the woman on top of another background, more beautiful one. So what we need to do here is to first generate what is called a bit mask. And with this bit mask essentially is having ones or zeros where the woman is, and having zeros or one around her. And the way of doing that, observe with this packed compare equal byte instruction. That's what this mnemonic here means. What we are doing, we are comparing each of these bytes, each of these 8-bit elements, blue, with the value that it's coming from the image. So from the image, this image, right? The input image with the woman. So if the particular pixel, these 8 bits are blue, we will put 1 in the output. That's how we generate the mask. If it's not blue, then we put 0 in the output. And now we are going to use this mask. So by the way, this is the sequential code that we would use if we want to do this in a sequential machine. We have a for loop. We have to go over all the pixels of the image from 0 to image size. And then we check, okay, the pixel that I just got from memory, this XI, is it blue or not? If it's blue, if it's blue, then I copy the corresponding pixel from the blossom background. The blossom background is the beautiful background here, and I put it in the new image. And if it's not blue, then it's because it's a pixel that belongs to the woman. So I take this pixel and I put it in the output. That's the sequential computation that we need to apply here, but we can do it much more efficiently if we use MMX instructions. So so that's more or less the flow of computation here. We need to, after having generated the mask with the previous instruction that we had in the previous slide, we apply this mask to the blossom image, which is contained in MM4, in this register MM4, and to the women's image, which is contained in this MM3. So we AND the blossom image and the woman's image with the mask, and then we obtain some output, and the only thing that we need to do is ORing the result of the previous operation. You have the entire code here. You can think yourself about how exactly works, but it's pretty simple, as you will see. And if you need a little bit more detail or a little bit more explanations, you can ask me right now, later, or read the paper. Is that fine? Okay, so then we are done with the SIMD processors, with the SIMD extensions, and now we are ready to start talking about the GPUs, which essentially is going to be to recall many of the concepts that yesterday and today have already covered, plus taking into account some other concepts that were discussed and presented in previous lectures. If I'm not wrong, in a previous lecture, we were talking about fine-grained multithreading. Do you remember that? What is fine-grained multithreading about? It's hardware that has, it's an architecture where we have multiple thread context. And for each thread context, we have one program counter and registers. So this means that on the same pipeline, we can execute several threads at the same time. And each of these threads, it's running its own code. So that's why in each of these threads, each of these threads has its own program counter and its own registers. And why is that useful? Because we can take advantage of all the pipeline cycles. Recall that one of the problems in pipelining is that if you are executing a thread, a sequence of instructions, and there are dependencies among these instructions, at some point you might need to stall the pipeline, right? And create some bubbles that actually are useless. So it's some cycles, some slots that we are not really using, but we need to have them to ensure that the program runs correctly. One way of dealing with that is having multiple threads running on the same pipeline so that we avoid the dependencies because each of these threads is running a different program. And that's essentially what fine-grained multithreading is about. And that's what you can read in detail in these slides. What we do in a fine-grained multithreading machine is that we switch to another thread every cycle, such that no two instructions from a thread are in the pipeline concurrently. So this means if I'm executing one instruction for thread 0 and another instruction for thread 1 and another instruction for thread 3, there is no dependence among all these instructions, so I don't have to worry about stalling the machine from time to time, you know, because there are no dependencies. So this way of executing instructions that you can find in fine-grained multi-threaded CPUs, like, for example, this one, where you see here in this one, how many threads can we execute at the same time? 4, right? Because we have 4 program counters. So we can have 4 threads, and each of the threads will have its own general purpose registers, as you can see here in the middle of the pipeline. So this way of using the pipeline by executing several threads in different stages of the pipeline, it's something that we are also going to use on GPUs. So now think about some of the concepts that we have already covered in the course. We started with pipelining, and we already know that SIMD processors use pipelining, right? And also GPUs, of course. All these functional units that we have in the GPU, they are also pipeline. We know that GPUs are a mix of array processors and vector processors. So they are SIMD processors in the end. And the last thing is that they are also going to use this fine-grained multi-thread execution, which means that I'm going to have like different streams of instructions executing in the same SIMD pipeline. And every cycle, I'm going to issue an instruction for a different stream. These streams of instructions are actually called warps, okay? And each of these warps has a certain width, which is typically 32, and it's more or less the same as the vector length that we were describing in yesterday's lecture. Okay, you can recall all these advantages and disadvantages by yourself. and now I think we are ready to start with graphics processing units. Why are they called graphics processing units? That's the first question to answer, because in the very beginning they were designed to run graphics workloads, right? They are highly parallel, same as the graphics that we need to generate for a computer display, and that's why this is their original name. But in the last decade, let's say, they have started being used for general purpose computation as well. And why is that? Because they have a lot of computing elements, and probably it's very useful to execute, I don't know, linear algebra computation, for example, which is also highly regular and highly parallelizable. Okay, GPUs are SIMD engines underneath. This is something that you already know. The instruction pipeline operates like a SIMD pipeline. It's more or less like an array processor. But it's not only an array processor, it's also a vector processor, because we have many processing elements that can execute different types of instructions, but then we will also have some specialized processing elements, as you will see later. The interesting thing here in GPUs, and recall one slide that we had yesterday where we talked about something that Fisher said in his paper, it's very difficult to program SIMD processors. One of the advantages of current GPUs is that the programming models has evolved in a way that these days is much easier to program them. So even though they are still SIMD engines underneath, SIMD machines, the way that we program them is not using vector instructions explicitly, but using threads, and this makes the programming much easier. We will talk also a little bit about programming later. So to understand this, let's go back to our parallelizable code, the parallelizable code example that we have been discussing in the previous lecture, in the beginning of this lecture. But before that, we are going to distinguish between two important concepts: the programming model, which is a software concept, and the execution model, which is a hardware concept. And why is that important? Why is important at this point of the lecture to be able to distinguish between these two? Because read the second sentence there. They are SIMD machines underneath, but we are not going to program them as if they were SIMD machines, but we are going to program them using threads. So what's the programming model? The programming model refers to how the programmer expresses the code, how we write the code. We could simply write a sequential code, just a sequential code, like this for loop that we have in our example, and we go over the 50 elements of the array and read one element, read other element, add them, and write to the output array, right? We could do that. And then we could have a very, very smart compiler that generates vector code for us. So what's a programming model? What's what the programmer has to do? Just writing sequential code. You know that, you understand that, right? So it's different how we program, how we write the code, and from how the code is actually going to be executed. So the programming model can be sequential, can be data parallel, can be data flow, can be multi-threaded. We can use something like pthreads or OpenMP and directly generate some multi-threaded code. And why not? Maybe we write a parallel program with OpenMP, but in the end, our CPU is just a sequential CPU, one single core. What is our CPU going to do? Well, running all the threads one after the other, right? So you already see the difference between a programming model and execution model, which is how the hardware executes the code underneath. And there we can have out-of-order processor, vector or array processor, data flow, multiprocessor, multi-threaded, etc. So the execution model can be different from the programming model. We can have a von Neumann model implemented on an out-of-order processor, or we can have an SPMD model implemented by a SIMD processor. SPMD means single program multiple data, and that's actually a multi-threaded programming model that is the one that we use on GPUs, and that's what the code that the programmer writes, and underneath the execution will be as if it was actually it is a SIMD processor. So that's why it's good to be able to differentiate these two. So how can you exploit parallelism here? We have our scalar sequential code, that for loop that we are using in yesterday and today's lecture. So let's examine 3 programming options to exploit instruction level parallelism present in this sequential code. The very first thing is the sequential or SIMD. The second one is SISD. The second one is data parallel or SIMD, and the third one is multithreaded, MIMD or SPMD. Recall that MIMD means multiple instruction, multiple data. SPMD is single program, multiple data. As you will see, they are kind of similar things. So the first one, programming model sequential. What do we do in programming model sequential? Nothing different than that. So we have our for loop, and we start running this for loop iteration by iteration. We need to first load from one array, load from the other array, add, and store. And then we go to the second iteration. This SISD program, this sequential program, can be executed on a pipeline processor, something that you already know, an in-order pipeline processor where we start issuing and fetching, decoding, executing instructions one by one. We can do this in an out-of-order execution processor where we can have some sort of instruction level parallelism. The processor starts issuing independent instructions because it has some instruction window that allows it to do it. And it's a kind of loop unrolling by hardware, as Professor Mutlu explained in the corresponding lecture. Or we could use a superscalar or VLIW processor, right? We can have something like this code, and then we have our smart VLIW compiler that extracts the parallelism there, generates some pack instructions, and then launches the pack instructions on the VLIW pipeline. So that is one possibility. We write a sequential code, and then we execute this sequential code on some specific hardware. And these are different possibilities for this specific hardware. The second possibility is using a data parallel programming model. And that's what we do when we vectorize code. Here we have our code, this is the sequential code, and suddenly we realize that these iterations are independent. I'm saying we, but it could be also a compiler, can be the programmer or the compiler. We realize that each iteration is independent, and because they are independent, they can be run in parallel, something like this, right? And for each of the instructions, we generate one vector instruction, and each of these vector instructions is going to be executed on the vector hardware or the SIMD hardware. So this is the vectorized code, vector load, another vector load, vector add, and vector store. So that's where are we going to execute this? Probably on a SIMD processor, right? But observe one interesting thing here. I could directly write something like that. Let's say high-level language code. I could write something like vector load, vector addition, vector store. And then I can have a compiler that generates code for this program to be executed on a sequential processor, for example. So today we will introduce a little bit of the CUDA programming language, which is a programming language for NVIDIA GPUs. But there is another very similar programming language that is called OpenCL. Have you ever heard about OpenCL? OpenCL is open, so it can, it's cross-platform, so and cross-vendor, so you can run it on NVIDIA GPUs, on AMD GPUs, but also on CPUs. And the way that you write this program is using an SPMD programming model. So you write parallel program, but in the end, you can have a compiler for CPU that generates the corresponding code for the corresponding assembly program with the corresponding ISA for a sequential machine. So it's another example of this difference between the programming model and the execution model. And then the third option, the third programming model is the multi-threaded. The OpenCL example could be a good one for this. Again, the realization is that each iteration is independent, and now instead of generating vector instructions, what we have here is like different threads running in parallel. So where could we execute something like this? We could execute that in a SIMD machine, because, for example, each of these iterations can run on each of the cores of a multi-core CPU, or this can also be executed on a SIMD machine, and that's what GPUs are. Yeah, this is another way of talking about, describing GPUs is single instruction, multiple thread architecture, but this is more like NVIDIA terminology, I would say. Okay, so a GPU is a SIMD or SIMT machine, except it's not programmed using SIMD instructions. I hope that this is already clear or starts to be clear. We program it using threads. It's a SPMD programming model, and each thread executes the same code but operates on a different piece of data. Each thread has its own context, and a set of threads are going to be divided or grouped into something that are called the warp or the wavefront. What is warp and what is wavefront? It's exactly the same. Warp is NVIDIA terminology, wavefront is AMD terminology. Over the rest of the lecture, we will talk about warps, simply because it's shorter. There's no other reason. Okay, and what's the warp? It's essentially a SIMD operation performed by hardware. And now, yeah, let's recap a little bit using this slide. How are we going to program the GPU? Using the SPMD programming model. SPMD is similar to MIMD. This means that I can write the code for every thread as if every thread were independent from any other thread, okay? But the truth is that the way that this code is going to be executed is on a SIMD machine. So what we are actually going to have in a hardware is a SIMD pipeline. So in the end, what we do is clustering these iterations, clustering these threads into something that are called the warps. What is a warp? In the case of NVIDIA, it's 32 threads. In the case of AMD, 64 threads. In the case of your exam question, sometimes will be 32, sometimes will be 64. The way that you have to reason is exactly the same. What do we do with these iterations? Each of them is assigned to a thread. And now, what the hardware will do is taking groups of these threads and putting them together in this warp. And when we start executing the instructions on the hardware, we will be issuing instructions for every 32 threads, for every warp. That's why here, now we no longer have something called vector instruction, but observe we have there warp 0 at PCX. So this load instruction is stored in a particular address that we have in the program counter. The address is X in memory, and this instruction is going to be executed for warp 0. Why warp 0? Because we are going to have more than one warp in each of the SIMD pipelines. So after executing this instruction, we will execute the next instruction, next load, again for warp 0, and then the next instruction is an addition, again for warp 0, and then the next instruction is stored for warp 0, okay? But recall, they are also multi-threaded machines, so we have no single warp. We are going to have more than one warp. So for now, only warp 0, but you will see soon that we are going to start executing instructions for many more warps. Okay, any questions until now? Okay. I think all these, so we are going to keep, let's say, iterating over all these concepts over the course of the lecture, so I think that they will be more and more clear every time.
When we say warp 0 and it is specified by NVIDIA as size 32, would this be the same as iterating first from I is equal to 0 to I is equal to 32 of the for loop all at once?
I equal to 31. We have yes, it's a good question. Very, very timely question. We have our for loop from 0 to n, right? And what are we going to do? We know the realization is that all these iterations are independent, so we can run them in parallel. So what are we going to do? When we write the CUDA program, the GPU program, what we are going to do is distributing all these n iterations among all the available threads. By the way, the threads are a software concept, so we can use n threads if we want. One single thread per iteration, right? And now we start executing the program on the hardware. And what's the hardware going to do? Say, okay, I have to execute n threads, but my SIMD unit, it's only 32. So let's take the first 32 threads, create one warp, and for this warp of 32 threads, I'm going to start executing these instructions. So iterations 0 to 31 will be warp 0, iterations 32 to 63 will be warp 1, and so on. Okay? Okay, let's have the break. Okay. We still have a few slides to cover, so let's continue. SIMD versus SIMT execution model. Let's start talking about more differences. SIMD, a sequential instruction stream of SIMD instruction. We have only one sequential instruction stream of SIMD instructions. In SIMT, we have multiple instruction streams of scalar instructions. And this is because we write the code for threads, okay? So that's why we say we have multiple instruction streams. And we talk about scalar instructions because that's the way we write the code, even though they will be later executed as vector instructions on the hardware. And there are two advantages of doing this. There are two advantages of using the GPUs or designing the GPUs in this way. The first thing is that we can treat each thread separately. So we can write code for every thread as if it was independent. And the good thing is, I mean, the very good thing of that, or the best thing of that, is that it's making programming much easier. That's the main advantage. But we talk about fine-grained multithreading of warps. Recall, we have already introduced the concept of warp. We already know that the warp in NVIDIA GPUs is 32 threads, and the GPU is a multi-threaded architecture. So recall, it's pipeline, it has some things, some concepts from vector processors, other concepts from array processors, and they are also multi-threaded processors. So in the previous slide, we were talking about warp 0, this instruction for warp 0, and this instruction for warp 0, and this instruction for warp 0. But the truth is that we have more than one warp. Actually, in the current GPUs, I think we can have up to 64 warps in the same GPU core, which is one of these extreme multiprocessors that you might be already be reading in the required paper. So the way that we are actually executing the instructions for the warps is in a multi-threaded manner. Let's assume that we have, let's say, 20 warps. What is the hardware going to do? We will have a warp scheduler, which is the unit that decides what's the next instruction to execute. Let's say that the next instruction is this load instruction. So what the hardware does is, okay, I have to fetch this instruction, this load instruction, and issue onto the hardware for which warp? In this case, for warp 0, which are threads 0 to 31. Recall the example that we had right before the break. And then we launch a new load instruction. And in this case, is load instruction for warp 1. Observe that this is warp 1 at PCX, and this is warp 0 at PCX. It's PCX because in both cases, it's the same instruction. They are executing the same code, right? So the load instruction is in address X of memory for both warps, warp 0 and then warp 1, and then for some reason, the warp scheduler decides to execute this instruction, which is for warp 20, and is this add instruction that is in PC X plus 2. And then next slide. But you see already how it goes, right? It's multi-threaded, so we start executing instructions from different warps in the same way as in the multi-thread processor that we saw in the beginning, where we were launching instructions from different threads. Okay. This is more or less the same thing. You have the SIMT pipeline where you have the functional units, and we start launching instructions from the different warps. Here you see the definition of warp, and you can figure out what's the reason why they decided to use that name. Okay. A little bit more detail about the architecture of the GPU. You should already be familiar with this figure as well if you have started reading the paper. Here we have the memory with the memory controller, different memory channels. Here we have an interconnection network, and on the other side we have the shader cores. These shader cores, this terminology, shader core, is coming from the graphics field. In the paper, probably they are called streaming multiprocessors, okay? And here in this class, we call them SIMT pipeline, okay? So observe that here is where we have our SIMT pipeline that actually is composed by, as if we had like 4 pipelines in parallel in this pictorial representation, but each of these is one functional unit, and they are pipeline. Somehow we have here, at least part of the pipeline. We have here the PC and the mask, because for each warp, we're going to have one program counter and one mask. Recall that we need the mask to do the predicated execution. We still have, of course, predicated execution and the GPUs. Here we have an I cache. It's an instruction cache where we store the program, the instructions that we need to execute, and here the decode stage, and then we issue the instruction onto the the SIMT pipeline. And with a little bit more detail, and here you can again see the multi-threaded execution of warps. So let's launch one instruction for warp 0 and then launch one instruction for warp 8. So this was 7, warp 8, warp 3, and so on. And we have our instruction fetch stage, decode stage. Here you can see the register, here the ALU. This is the memory, in this case the data cache, and the write-back stage. So this more or less corresponds to the stages that you already know, the typical stages that you already know in the pipeline. The exact detail is not like that, actually, but this is somehow simplified representation of the pipeline. But the important concept is there. Okay, recall the slide says, okay, you already know this slide, right? And now, instead of talking about vector processors, we talk about GPUs. And what do we execute in GPUs? We execute warps. And these warps have 32 threads. So if I want to execute this add instruction that I have there on a certain number of functional units, I might have 1 or I might have 4. So if I have 4 and I have 32 threads, how will I execute this specific add instruction on these 4? Well, I will start for thread 0, thread 1, 2, and 3 at the same time. And after that, I will start the execution for thread 4, 5, 6, and 7, right? You also know this slide as well. Now, instead of talking about vector registers, observe that here we have changed the labels here, and now these are registers of thread IDs 0, 1, 2, 3, 4, 5, 6, 7, etc. But the idea here is to show that this didn't change, right? It's still it's a SIMT machine underneath. And now also this slide going back to the idea of I have a certain number. My vector length was 32 in the example when I showed this slide in the beginning of the lecture. Now I don't talk about vector length, I talk about warp size, and the warp size is 32, but I only have 8 lanes, so I can only execute the instruction for 8 of the threads at the same time. So I need to do the entire execution for the entire warp in 4 cycles. But observe how here we are issuing this load instruction on the load unit for warp 0, and then one multiply instruction for warp 1, and then one add instruction for warp 2, and this one is for warp 3, and so on. So, and maybe right after finishing with this load here, maybe here I can run something for warp, execute something for warp 4, or maybe again for warp 0. This is something that the warp scheduler will decide. Okay. Yeah, and this is somehow related also to the example that we were discussing right after the break. We have this operation that we need to do wherever with some vector. In this case, n is 16, and what we do is dividing the computation among the available warps. Yeah, go ahead.
Yeah, in the last slide, we had the same, yeah, we've seen that before, but the thing is, if we have 8 processing elements, or SNMs, or however you call them, how can, if we only have 8, how can they do an add and a multiplication at the same time? Wouldn't they have to be split on to 8 different processing elements?
Yeah, so this doesn't exactly match whatever you have in the SM, in the NVIDIA architecture. I agree on that.
Okay, so it's not matching.
No, it's not exactly like that. But so essentially because multiplications and additions are executed on the same pipeline, those SPs that you can read in the paper. We're going to see them in a couple of slides. Let's go back to the question. Okay, so this was the idea, how we divide the computation. I have to operate on this array, and now, well, I write some code so that I assign threads to each of the iterations, but in the end, what the hardware is going to do is packing these threads 32 after 32 in warps, warp 0, warp 1, warp 2, and so on. And now a little bit more about the GPU programming model. We were talking about SPMD. The warps are not really exposed. We write the code for threads, and actually the way that we write the code is defining the threads. We define certain number of threads, but from the software perspective, and this is actually, assume that this is CUDA code, from the software perspective, we organize these threads into something called blocks, thread blocks. In OpenCL, I was talking about OpenCL before, they are not called threads and blocks, they are called work items and work groups, but they are essentially the same. And here, for example, if I want to define, let's say, 1,024 threads in total, I will have to group these 1,024 threads in smaller groups that are called blocks. And what's the size of these blocks? Whatever the programmer wants. Let's say, for example, 128. So if I tell you that my thread blocks, you see here, n block, n thread, so I will say, okay, the size of my block is going to be 128, and I'm going to launch, let's say, 4 of these blocks. So in total, I will have 512 threads, right? But now, I have 4 blocks of 128 threads. What is the hardware going to do with that? Can you guess?
Well, it will cut it down into its own size, right?
It's in its own?
Its own size, possibly because we only have 32 opportunities to elements, it will cut it down, right?
Exactly. So what the hardware is going to do, which each of this group of 128 threads that are called blocks, each of them is going to be mapped into one of the SIMD pipelines. And there, the hardware will say, okay, I have to execute 128 threads. If I divide 128 by 32, I have 4 warps. So now I have warp 0, warp 1, 2, and 3, and I will start executing instructions for warp 0, let's say the load instruction for warp 0, and then a load instruction for warp 1, and then a load instruction for warp 2, and so on. Okay?
Is it up to the programmer to find the correct block size? Because if we have a huge block size, we would have to run a lot of warps.
So there is an actual limitation of the maximum block size, which is 1024. But other than that, you could use whatever you want.
But it gets inefficient.
It gets inefficient if you use, let's say, 129. Okay. Why?
Because we have to reload it for just this one.
Exactly, because we would be using one entire warp, let's say warp 5, for one single thread. Let's say 31 lanes or 31 SIMD functional units will be completely unused because we only need to use one of them. So yeah, it's, let's say, programmer's responsibility to use, if possible, it should be possible almost always, a multiple of the warp size. Okay, actually, let's take a look at some code. This is our first approach to GPU code. Here we have, as usual, our vector addition. It's C code, or yes, it's C code, sequential code for CPU. We need to add element-wise these two vectors, A and B, and store the result in C. And what do we do if we want to translate this into CUDA or into OpenCL? Essentially observe that the body of this function, by the way, the functions in CUDA are called kernels, the body of this kernel is exactly the same. We are reading array A from array B. We are adding and storing the output in array C. But now, instead of having this II as the index of the for loop, what we have is this TID. And the TID is the thread ID. It's the number that identifies the thread among all the threads that are available and running on the GPU, on all the threads that the programmer has defined. Observe also that this thread ID is a function of the block dimension, 128 in the previous example, times the block index. So if I have 2 blocks of 128 threads, the first block will be thread from 0 to 127, and the second, what did I say? The first block will be from 0 to 127, and the second block from 128 to 255. And that's why I finally add this thread ID, which is the ID of the thread within each thread block. I guess that might be, must be clear. Here you have the same code with a little bit more complexity, I would say. I mean, it's not actually more complexity because this is essentially the same code. We are still adding 2 arrays, but instead of adding, so the 2 arrays are like a matrix, right? So it's 2 matrices. We are adding 2 matrices here because we have this double for loop here. But essentially it's the same. The good thing in CUDA and OpenCL is that we can define blocks of 1 single dimension or 2-dimensional or even 3-dimensional. So in this particular case, observe that we have thread index X, thread index Y, because we are indexing the threads in both dimensions and also the blocks. Unfortunately, we don't have time to go deeper today into the GPU programming language, but maybe we might have a chance in a later lecture. Anyway, if you are interested, just talk to me. And now let's take a closer look at what are called the streaming multiprocessors in NVIDIA terminology, but actually one of these SIMD pipelines, that is the way that we are talking about them throughout this lecture. And recall that we were saying the programmer defines blocks, but then when these blocks go to the hardware, I will map one of these blocks into one of these streaming multiprocessors, and what the streaming multiprocessor is going to do is decomposing these blocks into warps of 32 threads. And now, every time that we launch one instruction, we launch the instruction for one particular warp. You can already observe the difference between this SM here, which corresponds to NVIDIA Fermi architecture released in 2010, can compare it to the SM that you have in the paper, which is an architecture from 2006 or 2007. This is more complex, right? Instead of having only 8 of the SPs, 8 of the scalar pipelines, of the lanes, here we have 32, you see? These green little squares. The thing is that still, so here, the warps are executed, warps are still 32 threads, and they are executed on each of these groups of 16 SPs. So you need 2 cycles for the execution of the entire warp. So the good thing is that you can have one warp executing here, another warp executing here, and actually more than one, right? Because these are pipelines, so it's one warp every cycle.
When you say a warp is executed every 1 cycle, do you mean a new instruction is fetched?
A new instruction is fetched and issued on the pipeline, but then you have a certain width of the pipeline. If I recall correctly, it's kind of 24 pipeline stages. It's something like that. But also, going back to the idea of GPUs are a mix of array processors and vector processors. You remember that, right? And you were asking me, where do I execute the addition and where do I execute the multiplication? So additions and multiplications are executed here in the SPs. So from that point of view, these are kind of array processor, right? Because it's the same processing element can execute different instructions. But then observe that there are 2 more types of processing elements here. These are load and store. So these are load and store units. But then we also have these SFU. These are called special function units, and these are used for more complex computations, like, for example, transcendental functions, sine, cosine, and these kind of instructions. And also, another interesting thing is, instead of having 16, as we have here, we only have 4. So if we have 4, what does it mean? How many cycles do we need per warp? More than 2, right? Okay, so that's NVIDIA Fermi architecture. You can go and take a look at Kepler architecture, Maxwell, Pascal, and Volta, and Turing. And in each of these architectures, you will see some differences. Sometimes they have more SPs, less SPs. They are changing, let's say, improving the architecture from generation to generation, but essentially they are the same, or the way that they internally work is very similar. Okay, yeah, I think it's time to start summarizing on this. Traditional SIMD contains a single thread, sequential instruction execution. In warp-based SIMD, what we have is multiple scalar threads executing in a SIMD manner, okay? This must be already clear. Programming language, a programming model is not SIMD, it's something called SPMD, and it's the hardware, the responsible one for taking these threads and creating these warps and executing the instructions for these warps in a SIMD manner. A little bit more about the single procedure or single program multiple data programming model. It's a programming model rather than a computer organization. Each processing element executes the same procedure except on different data elements. It is possible to synchronize different warps at some points in time. We are not going to go into this detail. If we have time to talk in a later lecture about programming, we will talk about that. But yeah, you can have in mind that these warps, it's also possible to synchronize somehow if it's necessary in your program. And multiple instruction streams execute the same program. So recall that we would talk about advantages of SIMT. The first one was that each thread was treated separately because we just write the program as if they were individual threads. Another possible potential advantage is that we could flexibly group threads. This is not something, as far as I know, that real GPUs do, but it's something that could be implemented, and it's not that difficult. And you will see in which cases this can be useful. Yesterday, we were talking about predication. We were talking about the vector mask, and the reason why we needed this vector mask is because we want to write vector programs and also GPU programs where we can follow different paths of execution. Right? And instead of using branches, what we do is using, so these are the different paths of execution for four different threads. So in this type of SIMD architectures, what we do instead of using branches explicitly, what we do is using masks. So if, for example, I have, this is my warp. These arrows here represent each of the threads. And I have one instruction, first instruction, that is the same for the 32 threads of the warp, and then I have a branch, and I launch the branch for all the threads at the same time, but now some of the threads will go through path A, and the other threads will go through path B. And these threads, for example, these 4 threads go through path A, these other 4 threads go to path B, and then they reconverge and they continue the execution. So what's the problem here? I mean, how do we implement this in the real hardware? Using a mask. So in the branch, we generate the mask so that here we will have a bit equal to 1, here bit equals 0, bit equal 1, 1, 0, 0. So these instructions in this path are only executed by these 4 threads, those that have 1 in the mask, and then we will complement the mask and execute path bit for the remaining threads. So the way that we do this is by using the mask, but the problem, I think it's kind of obvious here. The problem is that because we have this divergence, we are wasting part of the resources, right? Because still we are, using the, I mean, the functional units are there, but we are not using them. We are not using the functional unit that is here or the functional units that are here. So the idea of grouping the threads flexibly, it's could potentially allow to have more efficiency in the execution. Consider 2 warps, warp X and warp Y, and they are ready to execute the same instruction, let's say 1 addition. But it turns out that they are going, I mean, the threads in these warps are going through different paths, and now we have that, let's say, path A, it's only going to be followed by these threads in warp X and these threads in warp I. What could I do? They are different warps, right? The proposal here, what we could do is merging these 2 partial warps, let's say. And we can do it in this particular case because the thread corresponding to this slot doesn't exist or is not going to go through the same path in warp X, but it goes in warp I, and the same for these slots here. So they could be occupied by threads belonging to different warps. So this would be a way of generating the warps flexibly, and in this way, when I execute this merge warp Z, I would be using more of the functional units, so I would be more efficient in the execution. In some cases, we will have kind of overlap, and we cannot completely merge them, so still we will need to launch 2 warps. That's essentially the idea that was proposed in this paper, and here you can see some nice example. So this, on top you have the baseline, and you see that some of the warps are incomplete, are running only, let's say, 3 threads or 1 thread here, etc. So on the fly, what the hardware could do is merging some of these warps. So for example, here, these two warps here, they can be merged, and these two can be merged and actually in a very effective way, and we end up executing the thing in a smaller number of cycles. So this could be something that, let's say, is not difficult to implement on a real GPU and could improve the execution of the warps. Yeah, this is for you to think, because observe that in the proposal, what we do is if, let's say, this slot here is free, and I have a thread in another warp that is ready to execute, I can merge these two so that this red thread, this red arrow, occupies the space that some blue arrow is not occupying, right? So that's how I get the merge warp. But observe that I need to have a match between one empty slot and one full slot here. The question is, could I move threads flexibly? So if I have a slot, empty slot here, but I have two threads that could go to this slot, could I move one of them to another lane? Think about that. There might be, it might be possible, but there might be more requirements, right? Because the registers corresponding to the two threads that I want to execute are exactly here in this lane. So somehow I would need to move those registers, the contents of those registers. I mean, it's just something for you to think. Here we have another, this is from another paper from our group with another way of improving the execution of warps. Quite interesting as well. And actually in this paper, there were proposed two solutions. One of the solutions of the hardware improvements were was for branch divergence. You already know what branch divergence means, because it's the thing that we have just seen in the previous slide. And the second thing is for long latency operations. What are the long latency operations? Here in the past lecture and in this lecture, we are talking about executing vector instructions or executing warps, and we see that this is very productive, right? We can achieve very high throughput because we launch one instruction and we will be obtaining one value, one result every cycle for an entire SIMT unit or for an entire vector, and seems to be like very, very efficient. But still the access to memory is a bottleneck. And why is that? Because accessing memory usually takes many more cycles than executing instructions on these SPs or SIMT pipelines, right? So memory accesses are long latency operations. And usually when we start executing a program, we will have to go to memory and get data from memory, and after getting the data from memory, we can execute addition, we can execute multiplication, and so on. So usually what happens is that we start computing something for different warps, and at some point we need to go to memory. And when we need to go to memory, we have a long latency. So for example, this is a memory request from warp 0 starts at this point, and then we need to wait for all these many cycles to get the values that we read from memory and bring them to registers, continue with the execution, and then for warp 1 is exactly the same, for warp 15, and so on. And what's the problem here? The problem is that the way that the GPU, within each of the SMs, within each of these GPU cores, the way that the warps are executed, or the instructions from each warp are executed, is in a round-robin manner. If I have 32 warps, I will start executing the first instruction for warp 0, and then the first instruction for warp 1, and then the first instruction for warp 2, and so on. And when I have launched the very first instruction for all the warps, then I go to the second instruction for warp 0, 1, 2, and so on. The problem with that is that if the first instruction is the same for all the warps, let's say an addition, all of them will execute this addition here. But at some point, all of them will start requesting data from memory. And this memory access takes much longer. So what's the problem? The problem is that I'm not using the cores, I'm not using the SIMD pipelines during a lot of cycles. Why is that? Because all the warps are accessing memory. Ideally, I could be using all these slots, all these cycles here by executing arithmetic operations, additions, multiplications on these cores. And this way, I could be hiding the latency, the latency of access to the memory of the GPU. But unfortunately, I cannot do it very well. That's the second problem that in this paper is somehow solved. But for the first problem, for warp divergence, what they propose is actually somehow similar to what we have already seen. Remember that in the previous solution, what we did is, okay, I have one warp of 4 threads, and 2 of these threads are not there, so I only have 2 of them which need to go through this path, and in the other warp I have 4, and these 2 are, and these 2 are not, so I merge them, right? And here, the proposal is kind of similar, but it's a different approach. Instead of merging different warps, what we do here is defining larger warps. Instead of having warps of, let's say, 32 threads, let's have longer warps with 128 threads. And then we are going to create kind of sub-warps, and we are going to launch the instructions for these sub-warps and in a dynamic way. So let's say that all of these ones and zeros that represent the threads that actually are going to execute one specific instruction. 0 means that we don't execute the instruction. 1 means that we execute the instruction. And the entire warp is divided in sub-warps. But the way that we create these sub-warps is by looking for ones and say, okay, let's launch all these 4 together, and then these 4 together, and then these 3 together. And this way, we can have more efficient execution, because we just need to launch, in this case, 3 instructions for 3 sub-warps instead of launching 16 instructions for 16 sub-warps of 4 threads each. Okay, if you are interested, you can take a closer look at the paper, and we can discuss it offline if you want. Going back to the long latency operations, what they propose is dividing the total number of warps, and instead of applying simply round-robin scheduling, what they propose is to group the warps into groups of warps, so that they apply like a double round-robin scheduling. First, they say, okay, let's schedule instructions for group 0 of warps, and then schedule instructions for group 1 of warps. That's what they do here. So they say, okay, let's go first for group 0. And we do all the compute instructions for the warps that belong to group 0. And then we start issuing the memory requests for all the warps, in this case, warps 0 to 7, which belong to group 0. And at the same time, we can be using the compute units, we can be using the arithmetic, the SIMD pipeline to run instructions for the warps that are in group 1. And when we are done, then we start doing the memory requests, in this case for warps 8 to 15, which are the ones to belong to group 1. So, and after that, more compute. And as you can see, we can overlap memory accesses, these memory accesses with compute here, and we can also overlap these compute operations with memory accesses here, and we end up reducing the total number of cycles. Okay, it's an academic proposal to improve the execution of the warps in real-world GPUs, and as you can see, it's pretty efficient. You can take a look at the paper if you're interested. We are very close to the end. Just want to show you a couple of pictures from real-world GPUs. This is NVIDIA GeForce GTX 285, was released in 2009. It's a pretty old one. This is the one that it's actually described in detail in this paper about NVIDIA Tesla. Observe that it says 8 SIMD functional units per core. These are the 8 SPs that you can see in each of the SMs. In the paper, they talk about streaming multiprocessors. Here we talk about GPU cores. So we have 30 GPU cores. Each of them has 8 SIMD functional units. Here you can see a more, let's say, pictorial representation of this. I really don't like this figure too much. I think it's more clear, the one that you have in the paper, and also in the slide that I showed you. And here you see the entire layout with 30 cores. And actually you can see how, in this graph, how the GPUs have evolved since 2009 until 2017. You can see, okay, so how much their power has increased, gigaflops from something, I don't know, maybe less than 1,000 gigaflops up to 15,000 gigaflops, which is quite an impressive evolution. And this is one of the most recent ones. This was released in 2017. And as you can see, it's much more powerful. Can compare the number of stream processors. In the previous one was 240. Here is 5,120. And this is the layout. You can find more information about this in the white paper that you can read in the slide, and also some blogs, NVIDIA blogs, like for example this one. As you can see, it has 80 of these GPU cores, so 80 of these SIMD pipelines that we have described in the lecture is each of these, and within each of them we have all these scalar cores, these SPs, which are the functional units. An interesting thing in this recent architecture is that they include some specialized cores that are called tensor cores, and they are specialized for deep learning to execute matrix multiplication very fast, somehow similar to, it's probably something similar to having a mini systolic array within each of these GPU cores. They are very optimized for matrix multiplication and for operations that are needed for deep learning. So yeah, it's kind of interesting hardware, and actually shows, you know, some trend that is pretty common nowadays in all computing systems is the heterogeneity of compute units, right? You see compute units here that are specialized for integer calculation or for floating point with 32 bits, for floating point with double precision, and also these tensor cores. So we need to have this heterogeneity to be able to run things in the more efficient way. And just like the last slide, to finish with this lecture, some food for thought for you to think. I'm not going to give you the answers. Compare and contrast GPUs and systolic arrays. The other day, Professor Muldo explained the systolic arrays, but also recall that he told this anecdote about some students from Toronto, the University of Toronto, who had taken a course about GPU programming, and they implemented a neural network on a GPU, and they were able to train a convolutional neural network pretty fast and go to a contest and win the contest. So that was possible, and the current development of deep neural networks and artificial intelligence is somehow very much enabled by GPUs, but also by new, recently engineered architectures like systolic arrays. What are they? What is better? GPUs, systolic arrays, and you can think which one is better for machine learning, which one is better for image vision or for image vision processing. What types of parallelism each one exploits? Something that you can think about. Recall, GPUs have array processor. So something from the array processor, from the vector processor, multi-thread architectures, pipeline architectures. and also what are the trade-offs of using one GPU or using one systolic array. So this is the type of questions that we continue studying and answering in later courses. The seminar in computer architecture that will take place in the fall semester and also in the spring semester in 2020, and the computer architecture master's course in the next fall semester. That's all from my side. If you have questions, we still have 2 minutes. If you don't have any questions, have a nice weekend. Thank you very much for your attention.